Hello everyone, my name is Zuzana Pinkushova and I'm a member of New Research Laboratory and Neuroanalytics Lab at the University of Strathclyde in Glasgow, where I'm completing my PhD. I'm really excited to present to you today revisiting neurological aspects of relevance, an EEG study which has been completed as a part of my PhD with my co-authors and PhD supervisors, Dr. William McGowan and Dr. Yasher Mushpeghi. This is my first ACAIN Symposium and I'm really looking forward to meet the community. I'll start this presentation with the introduction, where I'm going to define key terms from the title. Relevance is an important concept, but in order to understand it better, first we need to talk about information retrieval, which provides a context for relevance. So what is information retrieval? Imagine a user who has an information need, and they would, for example, like to know what's the best phone currently available on the market. So they ask, for example, Google, and Google then retrieves some documents from the collection of documents for the user to evaluate. So the user would see that, for example, first and second documents are ads, so they would skip them, but find the third document to be relevant in answering their information need. So what the user is doing by skipping irrelevant and interacting with relevant information is called relevance assessment. Relevance therefore plays a crucial role in the user-system interaction, and it is a substantial indicator of system retrieval performance and effectiveness. However, studying relevance can be challenging as relevance is considered to be multidimensional, dynamic, complex, difficult to quantify, and it depends on user perception of information relating to the specific information need situation at a certain time point. Relevance should be investigated as internal and subjective process, and that's why it's important to consider physiological, psychological, and behavioral aspects. No research employing neuroscience that emerged was able to address all these challenges and investigate relevance and intersubjective, systematic, and measurable phenomena that relevance is. This neuroscientific approach has significantly benefited the field of IR. The approaches to study relevance from neuroscientific perspective can be split into two groups. One that did consider information need and investigate the relevance within the concept of information retrieval, and the other group that investigated relevance in terms of word relatedness. Here we can argue that perhaps that's not the most appropriate way to investigate relevance, as relevance should be considered within the information retrieval. Therefore, in this presentation, we're going to mainly focus on the first group, so the one that consider information need and consider relevance as a part of information retrieval process. This line of research is called new research, and the first study that investigated relevance within the context of IR was Mushpeghi and colleagues in 2013. They used fMRI to investigate how does relevance happen in the brain. So they were trying to localize brain activity differences in the cortical regions during the processing of relevant versus non-relevant images. And they found differences in the regions of temporal, frontal, and parietal cortices. Later study, which was a follow-up of Mushpeghi and colleagues in 2018, found that inferior parietal lobe, inferior temporal gyrus, and superior frontal gyrus play a crucial role during relevance judgment. Increased activation of these regions for relevant items might have been related to visual spatial working memory. I mentioned neuroresearch studies that use fMRI, and now I'm going to talk about neuroresearch studies that use EEG to investigate relevance. So one of them was a study of Allegretti and colleagues in 2015 who were interested to find out when does relevance happen in the brain. So they examined the processing of relevant versus non-relevant images, and they found significant differences between 500 to 800 millisecond time interval, which you can see here in the figure. Next study is the Kim and Kim. In 2018, they investigated the relevance of video skims, and they explored the ERP associated with topical relevance of video skims and classified the data based on two specific ERP components, which were N400 and P600, which have been shown to be good indicators of relevant and non-relevant judgments. Our research aim is to focus on textual binary relevance assessment, using a data-driven approach to compare findings with previous studies and explore previously not reported ERP components. We based our research aim on facts that past studies examining relevance in the context of IR and therefore considering information need while employing EEG and focusing on textual information consumption, which is the most common form of information consumption online, has mainly used component-driven approach, but we're proposing data-driven approach, which has some significant benefits. For example, in comparison to component-driven one, it avoids potential analytical bias, it doesn't restrict previously reported ERP components, and it is able to detect potential components not previously reported. So what did we do in this study? In terms of apparatus, we used 128-channel geodesic sensor net. In our design, we use within subject design, during which participants perform question answering tasks. And the questions and answers we used were previously published and used in other studies, for example, of Moshfeghi et al. In 2016. So we used this data set and expanded it and adapted to the needs of our study because it has been proven effective in investigating relevance phenomena. For our variables, we had independent variable, which was binary relevance assessment, so relevant versus non-relevant, and the independent variable was the physiological or the EEG signal. We did control the number of relevant versus non-relevant question and answers. So we had 64 questions and answers, and then 32 of them were relevant and 32 of them were non-relevant. But we did not control the number of words that each participant has seen. So we left that on to the participant, as participant was able to, once they get enough information to judge the answer relevance, they are able to abandon the sentence presentation. And we have done that to simulate the real world information interaction. For our participants, in total, we had 29 participants. 4 of them participated in the pilot study and they were not included in the analysis. The pilot study has been done only to check that everything runs smoothly and the system is recording data appropriately and that the participants are able to understand the task. From 25 participants, we excluded 7 because of high number of physiological artifacts presented in their data. From 18 included participants, 11 were females, 7 were males, between 19 to 39 years old, with a mean age of 24.5 and standard deviation of 4.91. All participants are normal or corrected to normal vision. They haven't had any neurological or psychiatric disorder, and they were under no influence of drugs or medication. And we screen our participants using entry questionnaire to ensure that all the study requirements were met. In terms of language, 8 were native speakers, and the rest of the participants had high English proficiency. So we would present the participant with a question, then a fixation cross, and the answer presented word by word. And we use this approach because it has been previously used and it has been proven effective to minimize eye-related artifacts. So an example would be a question, what is caffeine? And then the fixation cross, and then the answer would appear such as caffeine, a stimulant, that. And then after participants gather enough information to submit their assessment, they will do that. So they will judge subjective perceived relevance of the answer. And after that, they can decide whether they would like to see the rest of the sentence or just terminate it and move on to the next question. For our analysis, we use data-driven approach, which has been effective in the whole brain analysis as it minimizes upfront assumptions. It also allows for the contribution of many distant areas at different time points. We took the values for 109 electrode pairs, compared them at every time point, so every 4 milliseconds, over the 100 to 750 millisecond time intervals of 0 to 100 milliseconds, and then time interval from 750 to 950 milliseconds were excluded from the analysis. And this is because we're not interested in the initial feature, stimulus features processing that was associated with the early time interval, and then also the late time interval was associated with large amount of eye-related artifacts and noise, so being excluded that because that was the interval where participants were submitting their judgments. So it was also motor movement as well. We then used non-parametric permutation-based PFT tests with 1,000 permutations, and we implemented that using StatConf function in EEG lab, and we considered differences to be significant at p less than 0.05. In terms of number of relevant versus non-relevant trials, as I mentioned in the design, participants were presented with equal number of relevant versus non-relevant question and answers. and their subjectively perceived judgments reflect that, because we do have approximately equal number of accepted relevant and non-relevant epochs after pre-processing. So as you can see, for relevant, the mean number of accepted epochs was 399.11, and then for non-relevant, that was 410.94. In terms of our results for the main findings, we found that the data-driven approach reveals significant differences in the P300, central parietal positivity, N400, and LPC ERP components, which is consistent with previous studies. Additionally, significant differences in the P100 ERP components emerge, which may signal early stages of selective attention allocation, with enhanced attention being paid to relevant stimuli. And that has not been reported by previous studies. Now, our study is the first one using data-driven approach to find this component. Let's talk about our results in more detail. So the first significant difference that we observed was within 100 to 200 millisecond time interval over the right central parietal region. And we see that the amplitude or the positivity was higher for relevant comparing to non-relevant content. And that was linked to P100 component, which signals initial visual field activation. The higher amplitudes for relevant content signal early selective attention allocation. The P100 component has been reported by previous studies to affect later ERP components associated with working memory, such as P300 or LPC. Another significant difference emerged within 250 to 300 millisecond time interval. It was related with P300 or central parietal positivity ERP component, and the amplitudes were higher for relevant comparing to non-relevant content. These differences might signal differences in effort to process relevant and non-relevant stimuli that is induced by differences in working memory load. Also, the components are linked to attention allocation, task relevance, and evidence accumulation during decision making. Next significant differences emerge within 400 to 600 millisecond time interval, and we see that the amplitudes were higher or more negative for non-relevant comparing to relevant content, and these differences were linked with N400 ERP component that is linked to aspects of semantic integration and lexical decision making. So relevant content is linked to higher semantic congruity, and therefore the amplitudes are higher. Another significant difference emerged within 600 to 750 milliseconds, and more positive amplitudes were associated with the processing of relevant comparing to non-relevant content. And these differences were also located over the right central parietal region and linked to the LPC component, which is associated with memory processing and decision making. So the effort invested in retaining relevant information during cumulative information exposure. In terms of further directions, we would like to further investigate the role of P100 component, since this is the first study that reported that in textual processing and relevance assessments. Then we would also look into relevance granularity, and we would like to investigate graded relevance using a data-driven approach, because so far graded relevance has only been investigated using component-driven approach, and we believe using data-driven approach might reveal some previously not reported differences as well. We would also like to look into contextual variables that might influence relevance assessment, such as, for example, considering cognitive context of the user. To conclude, our findings further the understanding of the concept of relevance and strengthen its theoretical foundations. Our findings confirm the findings of previous studies, so we also found P300 and CVP, N400 and LPC components, and then the data-driven approach revealed previously not reported P100 component that contributes to relevance assessment formation. Our study also provides better understanding of the nature of relevance assessment. I would like to thank you for your attention, and I would also like to thank my co-authors and PhD supervisors, and also big thanks goes to EPSRC for funding this study. I'm more than happy to answer any questions you might have. Feel free to email me or get in touch or follow me via Twitter, and I'll be really glad to hear from you.